Over the last several decades, a highly efficient form of surface extraction has steadily expanded across the ranges of central Appalachia. Mountaintop removal mining bypasses traditional tunneling. It requires clearing the timber and detonating the bedrock to rapidly expose the underlying coal seams. This sheer mechanical force releases high volumes of particulate matter, polycyclic aromatic hydrocarbons, trace metals, and hydrogen sulfide directly into the surrounding environment. Consequently, over 20 years of published observational studies have reported a disturbing epidemiological consensus. Papers routinely link the communities adjacent to these extraction sites with severe cardiopulmonary disease, elevated mortality, and congenital birth defects. To policymakers, the press, and the public, this dense wall of peer-reviewed literature appears to offer undeniable mathematical proof of a regional health crisis. To definitively settle the causality of these health impacts, the National Toxicology Program conducted a highly rigorous systematic review in 2017. This flowchart tracks their strict PRISMA filtration methodology. Starting with 4,356 references, researchers stripped away duplicates and irrelevant studies, tossing out hundreds of articles. The final yield was striking. Exactly 33 observational studies met the criteria. Yet even among this filtered group, the systematic review delivered a frustrating conclusion. The agency could not verify the community health effects due to severe systemic bias deeply embedded within the surviving literature. We are going to examine the structural flaws hidden within those 33 studies and dismantle the assumption that dozens of peer-reviewed papers automatically equal settled science. In environmental epidemiology, a massive volume of observational data cannot compensate for a weak methodological foundation. The most critical failure shared across the mountaintop removal literature occurs at the very first step, exposure characterization. The gold standard for environmental health is direct measurement, testing the exact dose of a contaminant entering a human body. But researchers bypassed direct sampling entirely, relying instead on crude proxy metrics. Rather than taking air or water samples, studies estimated a population's exposure by looking at county-level coal production tonnage or drawing a simple radius around a hospital zip code. The statistical consequence is severe. Out of the 33 community studies evaluated by the National Toxicology Program, 0 achieved a low risk of bias rating for how they characterized exposure. Geographic proximity is mathematically useless for determining an inhaled dose. It completely ignores microvariables like local wind direction, complex valley topography, and human movement patterns. Heavy dust and massive amounts of particulates are visibly and undeniably present at active excavation sites, but without verifying a specific mechanism linking that ambient dirt directly into the lungs of the specific individual studied, the causal chain is permanently broken. Documenting the existence of a hazard is epidemiologically useless if you cannot accurately measure the population's dose. This leads to a second methodological trap, overlapping datasets masquerading as independent scientific verification. Consider mortality. There is a cluster of 11 published studies that all report alarming elevated death rates near surface mining sites. However, these are not 11 independent findings. Tracing the citations reveals that almost all of them rely on the exact same national health datasets. This creates an illusion of replication. Researchers were simply mining the identical data pool 11 different times, creating an echo chamber of results rather than discovering new evidence. The fatal flaw here is that national datasets lack the granularity required to control for individual-level contributors to mortality. They cannot account for specific local poverty rates, access to care, or regional smoking habits. When multiple research teams amplify the same unadjusted dataset, they multiply the statistical noise. They do not multiply the scientific signal. We see the ultimate consequence of missing variables when we examine the most high-stakes claim in the literature, a severe spike in congenital birth defects near mining zones. This forest plot visualizes the findings of a highly publicized 2011 study by Ahern, which mapped the prevalence of birth defects in Appalachia. Ahern's data returned elevated prevalence ratios across multiple categories, specifically highlighting circulatory, respiratory, and central nervous system anomalies. These specific, terrifying data points fueled massive public outcry. To an outside observer, they provided undeniable proof of chemical harm to fetal development. But 4 years later, A 2015 reanalysis by Lamb investigated a critical, previously unmeasured confounding variable, the hospital of birth. In clinical diagnostics, not all facilities are identical. Different hospitals maintain vastly different pediatric reporting standards and sensitivities for logging minor congenital anomalies. Lamb corrected the methodological error. The Appalachian dataset was adjusted to account for exactly which hospital recorded the birth, neutralizing the diagnostic variance. Look at the results of the adjusted cohort. The black circles represent the newly adjusted data. They cling tightly to the 1.0 vertical baseline, indicating 0 increased risk. The statistical result was absolute. Once adjusted for hospital reporting bias, the elevated risk of birth defects in mountaintop mining areas completely vanished. In geospatial health research, failing to control for structural confounders will manufacture a public health crisis where none may actually exist. Stepping back, we can now see the aggregate findings of the 2017 systematic review regarding all 29 community health studies. The National Toxicology Program applied the OHAT risk of bias assessment tool against the entire body of literature, evaluating confounding, exposure, and outcome. The result is an overwhelming wash of yellow and red across almost all exposure and confounding cells, indicating high risk of bias. This matrix of compromised data is exactly why the systematic review had no choice but to declare the evidence totally inconclusive. The agency is not declaring that mountaintop removal mining is safe. They are stating that the current epidemiological toolkit used by these researchers is structurally inadequate to prove it is dangerous. The integrity of public health policy demands data that can survive strict, unyielding systematic scrutiny. To definitively answer the community health question, the scientific method applied to Appalachia has to evolve. The first non-negotiable requirement is the absolute abandonment of broad geographic and county-level proxies. Future studies must mandate granular, direct exposure characterization. This means actively monitoring indoor air quality and sampling exact residential drinking water sources. The second critical requirement is conducting controlled in vivo experimental models using the complex chemical mixtures gathered directly from the extraction sites. Combining precise individual human dosing data with targeted animal mixture testing is the only methodology that satisfies modern hazard identification standards. Until our measurement of exposure matches the precision of our health outcomes, the true human cost of mountaintop removal mining will remain lost in the statistical noise.